So far, for the inverse, we've learned what the inverse is, how to find the inverse if it exists, and then how to use the inverse to help us solve certain types of systems. So what we're going to do now is just develop a few properties of the inverse that are, they're fairly theoretical, but they help to shed um, more light on this idea of the inverse of a matrix, right? So let's take a look at some properties. And the first question that we're going to try to answer is this. Can an invertible matrix have more than one inverse? Is that possible? So could there be two matrices that have that property where when we multiply the matrix by both of them, we get the identity matrix? Well, the thing is, the answer is no, right? The inverse of a matrix has to be unique. Well, let's look at the proof of this, right? So here's our theorem, and it's a very simple statement. If A is invertible, so if we can invert a matrix, then A inverse is unique, right? So a matrix can have only one inverse. Now, the reason that I like to show this proof, other than the fact that proofs are fun, and in fact, proofs are what math is really all about. When you can describe when something has to happen, you don't get bogged down in the nitty gritty. You can see the global perspective. But how do you show that something is unique? And again, unique is just saying there is one and only one of those things. Well, a standard approach in math, when you have to show that something is unique, you assume that you have two of those things, and then you show that those two have to be equal. So, like, you make the assumption that, okay, let's say you do have more than one inverse. Then what we can do is if we can show that those two things have to be the same, then in fact there is only one, right? So let's start by saying, so assume that A has two inverses. And let's call them like B and C. So in other words, let's say that both matrices B and C have the desired property. So let's write down what those properties are. So if we start with B, remember what it says is that if you take A times B or B times A, you're going to end up with the n by n identity. That's what it means for B to be an inverse of A. But then if I'm saying that C is also an inverse of A, then I have another set of equations just like this, but instead of writing B, I'll write C, right? So these two things are known, right? Now what we want to be able to do is to show that B and C are equal. And it's just going to take a clever use of, algebra and all of this information right here to make the connection between B and C. So let's start with one of them. Now, what I know is this. I know that B, because of the properties of the identity matrix, I can write B as B times I, right? That's by definition. I is the multiplicative identity. So if I multiply any matrix by I, or I by any matrix, I'll get back that same matrix, right? So this is by definition. Next, well, I look at what I have up here. I have a few equations, right? I have a few equations that involve I and the other matrix C. So what I'm going to do is I am going to replace this I, right? Instead of writing I, I'm going to write A times C, right? So I'm going to replace this, and let's do that, because the second equation is saying I could replace it with CA, or I could replace it with AC. I'm going to choose the first one that I wrote down, right? So instead of writing the n by n identity, I'm going to write the product AC. So it's going to look like this. So AC. And now use my associative property. I know I can't just switch like the order, but I can change the grouping. So instead of grouping the last pair, I can group the first pair. And I can do this. I can choose to do the product as BA and then times C, right? That's the associative property of matrix multiplication, right? But then look at what the first equation tells me. Because B is an inverse of A, then this product B times A is also the identity. So what I'm going to do is now replace BA with I. So then I end up with I, right, times C. But by definition, the multiplicative identity times any matrix is that same matrix. So that is C. So here is that connection. So if they happen to be both inverses, they have to actually be the same matrix, right? So this shows that if you can't have more than two. That's essentially what this proof is showing, is that if you think you have more than two, then they in fact have to be the same. So this implies that B is equal to C, and hence the inverse of A is unique, right? So and A inverse is in fact unique, right? So that's our QED. Right. So this process, and when you think about the process that we use to find the inverse, it makes sense, because if we're going to use Gauss-Jordan, it doesn't really make sense to think, okay, I'm going to do the process one time and get a certain matrix, but yet do it another time with the same starting matrix A, and end up getting a different matrix for the inverse. It seems like, once the matrix is invertible, there's only one way, I can reduce it to the identity and therefore get its inverse, right? So it makes complete sense. But now this is the formal logic behind that intuition. All right. So that's the first one. Now, another one that seems like, okay, out of left field is this question. If A and B are both invertible, right? So are both invertible, what about the product AB, right? So the question is A times B also invertible? Right? So again, another way to ask this question is this: is the product of two invertible matrices another invertible matrix? And it turns out it's yes, right? Not only we'll be able to prove that the product is invertible, but we'll actually find a relationship. Like we'll have a formula for the inverse of this product in terms of these two, right? Now, the formula is going to be a little bit different, and I'll make sure that I give you the contrast between, what you know about properties of exponents and stuff with numbers versus what we're about to look at for matrices, right? So here is this theorem, and this has to do with the invertibility of a product of invertible matrices. So let's just say product of invertible matrices. All right. So again, notice how this question starts. It's the hypothesis here is that both of these are invertible. So if A and B are invertible, then AB is invertible. And here's the formula that shows us or tells us how to find the inverse. So if I have the product and I'm trying to invert this, what I have to do, and this is where it's a little bit different, I have to reverse the product, the order of multiplication, and then take the inverse of the individual factors. So the inverse of matrix AB is equal to B inverse times A inverse. And this is a little different from the our property of exponents that we know for real numbers, right? So let's look at a proof of this, and then we can sort of compare and contrast between what we know about reciprocals of numbers versus inverses of matrices, right? So let's take a look at this. Now, because we have, so what this is basically saying, if we write it out in words, is that the inverse of AB is B inverse times A inverse, right? Right. So, this statement, in fact, let me write it over here in blue. So this statement is saying, if we write it out, I guess partially verbally, the inverse of AB is B inverse A inverse, right? It's just, remember, all we use the -1, exponents, even though it's not really an exponent. Think of it as a superscript. The only thing we use this for in the context of matrices is to indicate an inverse, and that's what this is saying. This is saying that the inverse of AB is this thing. Well, how would I prove something like that? Well, why don't we just check to see if the definition of the inverse is satisfied? In other words, why not just take this and multiply this and see if we get the identity? And we would have to do it both ways, right? So in other words, since this theorem gives us the formula, the proof really just comes through verifying the formula, right? It's still a general thing. We're not going to write down a specific A and B and check it. No, we're going to keep it symbolic. But this is what we're going to do. So we're going to consider this product. What if I take AB and multiply, and let's put the AB in front and see what happens. So B inverse times A inverse. Because if this thing, right, that I just wrote down, if this product is equal to the n by n identity, right? And if it works both ways, if I put the AB on this side and simplify to the n by n identity, then in fact, yes, the inverse of this is this, and vice versa, right? Well, how do we simplify this? This is where the associative property of matrix multiplication comes in again. Because what I can do, as long as I don't change the order, right? Instead of, having like either this pair first or this pair, I can choose to group the middle pair. So in other words, I could do this. So this is B times B inverse, right? But again, because B by itself is invertible, we know that this, well, first of all, we know that B inverse exists, right? And this product is going to be the n by n identity because I'm multiplying a matrix by its inverse. So this is A times IN times A inverse. But then again, I can choose to multiply either pair, either the first pair or the last pair. I hope you're starting to see how important that associative property is, something that we take for granted. It's giving us the ability to really see what's going on with these more abstract ideas, right? But if I group the first pair, so if I choose to do that product first, then I know the product of A times the n by n identity is still going to be A. And then what I'm left with is A times A inverse. And again, by definition, this simplifies to the n by n identity, right? And that's what we would expect, right? If in fact these two things are inverses of each other, then we would expect that when we multiply them, the product simplifies to the n by n identity. But again, this is only partially complete. We have to consider the product where we put AB on this side. So put the B inverse A inverse first, right? Yeah, let me write it like this. So if we put B inverse times A inverse first and then times AB, again, group these, right? Just like we did here. The only difference is that instead of having the B and the B inverse cancel out first, it's going to be A and A inverse. So I'm left with this. I'll have B inverse, and then I have A inverse times A, and then times B. And then by definition, A inverse times A, that's the n by n identity. And then I bring this factor down, and this other factor down. And again, we group. So over here I group the first pair. Doesn't matter. Let's group the second pair. So this can be paired up like this, and the identity times B is going to be B. So I have B inverse times B, and again, that gives me the identity matrix. So what this shows is this is the special matrix that when I multiply AB by either before or after, it reduces to the n by n identity. So therefore, let's first write it in words. The inverse of AB is this product, but it's in the reverse order of the inverse of B times the inverse of A. So the inverse of the product is the reverse product of the inverses. So like this. And again, so now the shorthand way of writing this is that AB inverse is equal to B inverse times A inverse. And that's our QED, right? And again, the order here is important because if I do, you see, if I don't have it kind of this switched way, then the grouping in the middle wouldn't work out, wouldn't necessarily work out, right? And I know I can't necessarily just switch the order because in general, matrix multiplication is not commutative. So for instance, the product AB is not necessarily the same as the product BA, right? Now, as I mentioned, there is a version of this for real numbers, right? So for real numbers, basically, it's this. If x and y are real numbers and neither of them are 0, right? I mean, and that's the condition for finding the multiplicative inverse of a real number. You just have to make sure that the number isn't 0. So if we say that x is not equal to 0 and y is not equal to 0, then you might remember this kind of property of exponents that says if you have the product of two numbers and you're trying to, say take the reciprocal of these, well, it's the same as doing this. Right? And with real numbers, because real numbers under multiplication commute, then yeah, this is the same as y inverse times x inverse, right? We can do this for real numbers, but we can't do it for matrices. And that's why we have to have it in this B inverse times A inverse pattern. Now, here's a corollary of this theorem, and a corollary is just usually an extension, or sometimes it just kind of goes a little in a slightly different direction than the theorem, but it follows really directly. Now, what happens is, so this theorem here, we illustrated the proof when you just have two matrices, two invertible matrices. Let's say they're both n by n. Now we want to know what their inverse is, and this formula tells us how we can find that inverse. But what if you had 3 invertible, or 4 invertible, or 5 invertible, or n invertible? So this is what the corollary says. If A1, A2, ... AN are all invertible matrices, right? So are all invertible matrices. Then the product of all of them, again, assuming that they're all of the same dimension, so the product makes sense, the product is well defined, right? So if these are all invertible matrices, then A1 times A2 times ... times A sub n, that product, right? So then this product is also invertible. Right? And we can use this formula as an extension of it. So if I need to find the inverse of this product, I have to take the reverse, or the reverse product of each of these factors. So it will be my A sub n to the -1, and then it would be the one right before that, which would be with a subscript of n minus 1, and then ... all the way down to 2, A2 inverse, and then finally A1 inverse, right? Now, to prove this, when you have you don't have a fixed number here, you'd have to use something like mathematical induction. So if you're familiar with mathematical induction, this would be a nice exercise to say, hey, let's think about how induction would allow us to prove this for any n, right? So I'm not going to give you that particular proof. I know not everyone is familiar with induction, but if you are, it's a worthy exercise to think about, right? All right, we got a couple other properties now. Now these properties take us back to linear systems. right? And you know it. So I'll just state this particular theorem, and this has to do with the uniqueness. I left out my uniqueness of solutions to linear systems, right? So of solutions to linear systems. And the question is, so let's say we have a system and our coefficient matrix is square. So we have the same number of equations as variables. Well, it turns out that if the coefficient matrix is invertible, then you have to have a unique solution, right? So here's the theorem. So if uh, A is invertible, right, then our matrix equation AX equals B, right? So then that matrix equation AX equals B, again, and here we're assuming that the multiplication, everything is compatible. We would be assuming that, A has, since A is an n by n matrix, it would have n columns, and then we would assume that X would have the n rows and so forth, right? So then this equation has a unique solution, right? And then we can actually write it down. Now, that's the process we actually developed or mentioned in the previous video. This is now essentially just giving the formal proof to say that yes, we'll always get a unique solution, right? And it's just a few lines, right? So since A is invertible, and by what we did previously, we know that A inverse is unique, right? So A inverse is unique. And then, yeah, we just go through and essentially represent the process symbolically. So if we start with our AX equals B, if we multiply both sides by this unique inverse, right? So if we have A inverse times the left-hand side, well then that would have to be the same as A inverse times the right-hand side. And again, use the associativity property. So associate the first pair like this. On this side, since there's the product of just two matrices, there is no ambiguity about, okay, well, which operation do you do first? Well, there's only one operation on this side. So I'll just write it like that. And then we know that this, by definition, is the n by n identity. And then it's times x, right? And that right-hand side doesn't change. And then what happens is the identity times x is still x, and therefore we have this. So because now we can say with certainty that A inverse is unique, then this represents a unique product. So therefore the solution has to be unique, right? So therefore x is unique, right? So going back to linear systems, when we think about the three possibilities for a linear system where you could have no solution, a unique solution, or infinitely many, if the coefficient matrix is square, now we have something tangible to say, I know what has to happen. So without even doing any of the Gaussian elimination, right? I know what has to happen for the system to have a unique solution. That coefficient matrix has to be invertible, right? Okay, so that's our QED, right? The final one is related to this, and it's the other special type of system that we haven't really done a lot with up to this point, right? But it's the homogeneous system, where all the constants on the right hand side, right? So that like in the augmented matrix form, where your final column is filled with zeros, right? Remember what we had said is that those systems are always consistent, right? Um, so what happens in that case if we have a invertible coefficient matrix on this side and we have essentially the zero matrix on this side, or the zero column on this side, right? And the theorem is this. So the notation that we utilize to indicate in the matrix form, to indicate a homogeneous system, we just use like a big zero right there, right? To say, okay, this whole thing on the right hand side is filled with zeros. It could be a single column, or it could be more. It could be a matrix that has multiple columns, but we just use the big zero to indicate that yes, all the entries in whatever matrix on the right hand side, all those entries are zero. So the thing is, this system, this homogeneous system, right, has only the trivial solution. And remember, the trivial solution is where all your variables have to be zero. So this has only the trivial solution if and only if the matrix, the coefficient matrix, is invertible, right? So it has only the trivial solution if and only if A is invertible. And this proof is even shorter, because what happens is, look at it this way. If we utilize the formula from our previous theorem, and now we have, like, let's say a column of zeros, and you're multiplying it by your inverse, well, when you do your row times that column, right, each row times that column, you're just going to be adding up zeros. So you're going to be left with x equals 0, right? So really short proof, right? So again, if we start with this, and then by what we just proved above, that since the matrix is invertible, right? So if your matrix is invertible, then you're going to have that your x is equal to A inverse times the zero column, or the zero matrix, which then tells me that x itself has to be the zero column, or the zero matrix, right? Now, essentially, what I've only proven one direction of this statement, to say if the matrix is invertible, then the homogeneous system will always have just the trivial solution, right? I'm not going to prove the reverse. You can think about what that might mean, to say if this system only has a trivial solution, then how can we conclude that the matrix is invertible? So there's a little thing for you to think about. But this proves one direction, and this is the direction that's most useful for us at this point, right? So that's our QED, right? So there are a few uh, properties that are related to the inverse, and I think many of them we just kind of solidify our intuition about the inverse and how it can be used, and certain properties, especially with the product of two invertible matrices being themselves invertible, right? So I hope you found that interesting, and if you like proofs, there are tons more that we can work on, and maybe we will in a future video. See you then.